Hello. So far in our autonomous agents lecture, we discussed several different behavior patterns, but they were all applied to a rather small group of intelligent agents, just like in our fox and rabbit example. But what if we add some AI to a multi-agent system, like a really large number of intelligent autonomous agents? And the answer is we get swarm intelligence. It's defined as collective behavior of decentralized, self-organized system. This behavior arises through interactions among agents that themselves do not exhibit such a behavior. Just like this nest created by thousands, perhaps millions of termites. The structure is known as a termitry or termitera. But any individual termite doesn't exhibit any particular construction skills. But working in a large group, really large group, they display this new behavior of creating quite amazing and actually also quite complicated structures. Populations of agents in swarm intelligence interact only locally, usually within some radius, so just with agents that are closest to them, not the entire group. And these agents follow usually very simple rules. So you may say that autonomous agents in swarm intelligence are quite stupid. Moreover, there is no central control, no central brain steering them all. And still an intelligent global behavior emerges in this system somehow. Swarm intelligence may be artificial or may be natural, such as insect colonies, but also bird flocks, animal herds, fish schools, and so on. In AI, they appeared for the first time in 1986, proposed by Craig Reynolds, that's this guy in the photo. And the system proposed by Reynolds is known as Boids, bird androids. Boids, okay? Boids are quite popular in games technology, but also in film, for example. The armies in the combat scenes in Lord of the Rings were created using this technique, Boids. So, how does it work? Each individual here is governed by three rules, and it is important that these rules are only applied to its closest neighborhood, not to the whole flock. And these are separation, steer to avoid crowding local flockmates; alignment, steer towards the average heading of local flockmates; and cohesion, still to move towards the average position or center of mass of local flockmates. And here is a natural version of a flock of Boids, because sometimes you have to stop playing games and go out for nature. These are tens of thousands of oyster catchers and knots I filmed a few years ago in Snettisham, a bird reserve in northern Norfolk. Ecosystems are another example of an emergent system, and a very well balanced one. This balance can be achieved thanks to something that is called a negative feedback loop. And it can be explained on the example of predators and prey. When there are many prey, the predators will find food very easily. The number will increase, however, the more predators means fewer prey. The prey population will decrease. At some moment, there will be too many predators and the whole situation reverses. Now the predators won't find enough food and their population will decrease. With fewer predators, more prey will survive and their population will rise again. This situation of negative loop is quite popular in games. For example, in Civilization, growing cities will lead to growing population that will demand more and more food, and eventually the city's size will be stabilized at a level in which the city can be supported by the terrain around it and the current level of technology. Apart from negative feedback, we also have, I think it's not a surprise, positive feedback. An example can be found in chess. If you take many pieces from your opponent, you make the opponent weaker and weaker, and it will be even easier to take even more pieces after a time. These two types of feedback loop are commonly used with complex agent systems as an effective self-regulatory tool. This concludes the lectures on autonomous agents. Our next AI topic is pathfinding. You will find the link to the first part somewhere here. And now I thank you for watching and goodbye.